So pH of less than 7, that's acidic. Again, if it's right on 7, that means the same as water, neutral. Neither acid nor base. They're equal. They are canceling out. And if it's above 7, that means it's basic. So if the pH is 8, 9, 10. So our scale basically goes from 0 to 14. So 7 is neutral. From 0 to 7, that's considered acid. From 7 to 14, that's considered basic. Okay? Now, this is a log scale. You may have heard the log called the base 10 log in the past, maybe in a class or something. So, 10 to the negative 7th gave you 7. 10 to the negative 6th would have gave you 6. 10 to the negative 5th will give you 5th. So that means every change in pH is not just a small amount of difference, it's actually 10 times more acid. Because it's 10 to the negative 7, it's 10 to the negative 6. So a change from pH of 7 to 6 means there's 10 times more acid. 7 to 5 would be 10 times 10, 100 times more acid. So a slight change in pH is really 10 times, 100 times, 1,000 times more acid. So here's a little chart I think is kind of interesting. If you can see that. So here's water right in the middle, neutral, 7. So if we go up, okay, these have more acid. So milk actually has a little bit more acid than water. 6.4 is the pH. And then bread, actually 5.5. Coffee, 5. Okay, think about that. From 7 to 5, that's actually 10 times and 10 times. So there's actually 100 times more acid in coffee than there is just pure water, for example. Keep going. Tomato, 4.2. Apple juice, 3.8. Sodas, 3. Okay, 7 to 3. We went 10, 100, 1,000, 10,000 times more acid in soda than there is pure water, right? Or 1,000 times more in soda than there is in coffee, right? So I'm saying it's a big deal, right? To go from a change of 1 pH is 10 times more or less acid. And the other way, how about base? Well, you know, blood is slightly basic, seawater, milk and magnesia, bleach, things like that. So that's kind of a big, broad scale. Okay. So I want to discuss how to do Sig Figs, because Sig Figs are a little odd with logs, but they make sense once you think about it, I think. So, the base 10 log, what the log key does is it basically takes away the 10. So when you do this, negative log of 1 times 10 to the negative 4th, if you try it on your calculator, you're going to get 4. Just like negative log of 1 to the negative 7 gave you 7. The log key just taketh away the 10 there. And then you do negative log, which makes that negative go away, and it just becomes 4. So negative log of 10 to the negative 4th is 4. Negative log of 10 to the negative 7th you saw was 7. Negative log of 10 to the negative 10th would be 10. So that means that number out front, that 4, that 7, that 10, that came from the exponent. That was not determined by any kind of significant digits. Just that exponent became that number out front. So again, the last one, 10 to the negative 7th became 7. Are you with me? Does that kind of make, right? This number, the 7, the 4, whatever, came from this exponent. So it was not dependent on the Sig Figs at all. These are our Sig Figs out front, whatever's out here.
So why is it not the other two? Why is the both?
Okay, 1 second. I'll show you. Because it's not a 1 any longer. So this determined this to be 4, 7 determined that to be 7. So these are our Sig Figs we know, right? So this is not right. We know, 1 Sig Fig times 10 to the whatever. So this is my 1 Sig Fig here. So my 1 Sig Fig, I show it as a decimal place over here. So since I had 1 Sig Fig here, I'm going to have 1 decimal place here. Because again, the 4 came from the exponent. It did not come, anything had to do with Sig Figs. It's just because the log turns the 10 into the base number. So let me draw a little arrow here. This determined this, which means 1 Sig Fig here gives me 1 sig fig here, or decimal. Okay, how about the next one? Crystal was asking, well, if that's true, then why isn't that just 6? If it was 1, it would be just 6. But it's not 1, so it's going to be something close to 6, but not quite. So it's 5. But still, the exponent is determining this number, which means these 2 sig figs here, right, 8.0, that's 2 sig figs. That tells me put 2 decimals after it here. Okay, let's try that out. Try it out in your calculator. Try negative log of 8 times 10 to the negative 6. Make sure you get 5.1. Let's try it out. Negative log of 8 times to the negative 6. So it's going to be close to 6, but not quite 6 because it's not a 1. If it was a 1, it'd be exactly 6. But. So did you get 5.1? Yes? Okay. Remember, since it was 8.0, 2 sig figs, it's going to be 5.10, 2 sig figs. So again, this is not a sig fig because this came from the exponent. This is not a sig fig because it came from the exponent. That's a sig fig, so that's a sig fig. That's 2 sig figs, so that's 2 sig figs. Do you have something written down about that? That's going to bite you in the butt. Yes?
So whenever I got 5.096, it says 2 sig figs packed in decimal place. So what would it be 5.01?
096?
Yeah, I got 5.096.
It's going to be 10. The 6 makes the 9 round up to be.
Okay.
Right? Where's my.
Yeah.
Okay, you got it?
I'm stupid, yeah.
Yeah, so this rounds up, so this rounds up.
Yeah.
Right. Yeah. Yeah. Okay. And the next one, did you get 7.62? Negative log of 2.46 negative 8. Okay. Okay. Oh, negative 8. If it was a 1, it'd be 8, but it's not a 1, so it's going to be something close to 8. It's going to be 7 something. So this determines that. So now, 2 sig figs, so 2 decimals, 2 sig figs. Okay, let's try a couple. So, get out your handout. Hopefully you got your handy handout. Let's try pH of coffee. What's the pH of coffee if the hydronium is 1.0 times 10 to the negative 5th? That one's easy. You don't even need your calculator. If it's 1 times 10 to the negative 5th, it's going to be 5. But 5 point what? How many decimal places will it have? How many sig figs are there in front of it? 2, so I'm going to have 2 decimal places. So it's going to be 5.00, right? Okay, I'll just write it out anyway, but the pH would be the negative log of 1.0 times 10 to the negative 5th. So 5.00, yes. So again, these 2 sig figs here give me 2 decimals here because this determined this. Are you with me? Mm-hmm. Awesome. Try the next one, tomato juice. If you're in Scotland, tomato. Not tomato or tomato, tomato. 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 Okay, negative log of that. Figure out the sig figs. Ask your neighbor. Find somebody next to you, across from you, around you. Is it what? No, it's pH. No, pH is no. It's molar here. Yeah, that one's molar. pH is not. Yes. You had a very good question. There's no units on pH. Good question. There's no units on pH. Yeah, it's just 5.00 or whatever. And then pH equals 5.0. Yeah, it's not molar or anything. So compare it. What'd you get? 1 decimal, 2 decimals, 3 decimals, 4 decimals. Talk it over. Let's hear it. See what you guys got. 3.674, she says. What do you think? Should we stone her? Is she okay? Yeah, that sounds good. So 3 sig figs here. So 3 decimals afterwards, right? So, bleep, bleep, bleep. Try that again. The pH of negative log of 2.12 times 10 to the negative fourth molar, 3.674. Awesome. Great. Okay. Okay. Here's a thinker. The hydroxide is 1.0 times 10 to the negative 3. What's the pH? So, now I don't have the hydronium, I have the hydroxide. But I know how to find the hydronium from the hydroxide. What do we do? What did I just show you? Right, the hydronium times the hydroxide has to equal 1 times 10 to the negative 14th. So if I know the hydroxide, then I can find the hydronium, and I can just do the negative log of whatever that is. So try that out. So you have the hydroxide, so find the hydronium, and then do the negative log of that. Let's try that again here. So the hydronium times the hydroxide equals 1.0 times 10 to the negative 14th. So the hydronium must be 1.0 times 10 to the negative 14th divided by 1.0 times 10 to the negative third. So the hydronium must be 1.0 times 10 to the negative 11th, right? And then the pH is the negative log of 1.0 times 10 to the negative 11th. So 11 point, again, yes, 2 here, so we're going to have 2 here, 0, 0. Okay, great. Okay. Try a few the other way. So, pH is the negative log of hydronium. Let me write that down here again. pH equals the negative log of the hydronium concentration. So what's the hydronium concentration? Well, I would move the negative over to make it negative pH. And then to get rid of log, I have to do anti-log. So look on your calculator and see what's printed. See what's printed just above your log key. Should be 10 to the x. So I told you the log key actually taketh away the 10 to the anti-log puts back the 10 to the. So the anti-log giveth the 10 to the log taketh away the 10 to the. So you see the difference there? So the anti-log is really 10 to the negative pH. Anti-log of negative pH. So the log takes it out, the anti-log puts it back. So let's try this. So the hydronium would be anti-log of negative 8.00. So try that on your calculator. Basically 10 to the negative 8th, you can tell. But negative 8, anti-log, what did you get? Something times 10 to the negative 8th? 1, yeah, probably 1. Question is, though, is it 1? Is it 1.0? Is it 1.00? So now I'm going to do the Sig Figs backwards. Yes, because we learned that these two here came from the two out front, right? Now we're doing it backwards. Right? So this determines this. So it must be 1.0. The other way, 2 of these means 2 decimals. Now it's the opposite. 2 decimals means 2 Sig Figs here. Now we're just doing it the opposite way. Right? Just doing it the opposite way now. It was 2 Sig Figs is 2 decimals. Now it's 2 decimals means 2 Sig Figs. We're just doing it the opposite way. Okay, try the next one. If the pH is 3.7, what's the hydronium concentration? 4 point what? 6.7 times 10 to the negative 13th. Oops. Yeah, that sounds right. Again, 3 decimals, so 3 sig figs in front. And that 12 point tells me it has to be negative 13. Because again, it would be just a little bit bigger. And then molar. Again, 3 sig figs here, so 3 decimals, or 3 sig figs there. 4.67 times 10 negative 13. Pardon me, okay. Okay, so I want to show you a couple of reactions now with some acids. The first one I'm going to show you is a simple single replacement. Remember that, where you just take one thing moves? Remember, single replacement? So you see in these, potassium plus hydrogen with nitrate. You see the nitrate moves over to go with the potassium, right? Can you see what that happens here? Let me doodle here. All right, so this moves over with the potassium. And it makes potassium nitrate, right? And then it leaves hydrogen by itself. Well, hydrogen by itself is one of the diatomics, so it winds up becoming H2. Same thing with magnesium and nitric acid. Oh, again, I move the nitrate over, and I make magnesium nitrate, which is Mg. It's 2 plus, nitrate's 1 minus, so I need 2 of them. And again, hydrogen by itself, so H2. So that's the most simple reaction. So there are lots of metals that will actually dissolve into acid. And we saw this in our lab with our gas lab, where we had the long tube we had called the eudiometer, and you poured the acid in the bottom, put the food coloring in it, it was kind of pinkish, and then you filled it with water, and then you took some magnesium metal, remember, on a wire, put it in the end, and you turned it over. The acid came down, reacted with the magnesium. That's what happened. The magnesium itself dissolved into aqueous, and then it made hydrogen gas that bubbled out. Remember that? So that was that reaction, basically. Although ours was HCl, so it made magnesium chloride, but still the same kind of deal. So that's the basic pattern. So single replacement. So one thing, the anion moves from the hydrogen to the metal. So the nitrate moves, the chloride moves, the sulfate moves, whatever it is your acid's with, okay? So that's one. Now another common reaction is with carbonates, CO3 2 negatives, or bicarbonates, HCO3 negatives. These are going to be double replacement reactions. So remember double replacement? Now we have 2 things changing partners, right? Remember 2 things move. So I'll show you an example. Let's look at this one. Calcium carbonate plus hydrochloric acid. So if you were to do that double replacement reaction, if you were to write that down, you would predict, okay, well, double replacement. So the carbonate anion and the chloride anion, those are going to swap partners, right? Because it's double replacement. So 2 things move. Oh, so I'm going to put calcium with chloride, and I'm going to put hydrogen with carbonate, make carbonic acid. Right? You'd predict that, I hope. Would you predict that? Right? Double replacement. Oh. Give them new partners, right? So put the chloride with the calcium, put the carbonate with the hydrogen. Hopefully you would predict that. Double replacement reaction. Okay. Well, the only difference is this is carbonic acid. Carbonic acid is really, what it really is just carbon dioxide that has actually dissolved into water. So whenever you write a double replacement reaction and you see carbonic acid, we're going to scratch it out, or you can erase it, or whatever, and we're going to replace it with what it really is, which is carbon dioxide gas dissolved in water. So we're just going to mark it out, or erase it, or whatever, and just write, oh, H2O liquid and CO2 gas. So, I'll say it for the 3rd time. Whenever you get H2CO3 aqueous as a product, get rid of it and replace it with H2O liquid and CO2 gas. If you had, let's say you had, it was balanced and it was 2 H2CO3s, then you get rid of it and you would make 2 waters and 2 CO2 gases. If it was 3, you make 3 waters and 3 CO2 gases, or whatever it was. Okay, let me show you another one. 2 sodium bicarbonate with sulfuric acid. Okay, so we're going to take bicarbonate and sulfate. We're going to swap them. So I'm going to make sodium with sulfate and hydrogen with bicarbonate, make carbonic acid. And I balanced it already for you, so 2 of these makes 2 of those. Aha! Ding, ding, ding. Whenever I see that, I know get rid of it and replace it with what it really is, which is water and carbon dioxide gas. But it was 2, so I'm going to make 2 waters and 2 carbon dioxide gases. Okay? So, hope you have a big note written down. Whenever you see this in interaction, just go back, erase it, or scratch it out, or whatever, and just write instead what it really is, which is carbon dioxide gas dissolved in water. Oakley dokley. Let's try a couple reactions here. Just predict some products here. Let's look at this one. Zinc, metal, and HCl, which we now know is hydrochloric acid. So let's predict some products. So I have a metal and I have an acid. So that's going to be, we said, a single replacement reaction. So what is going to move over from the hydrogen to the zinc? The chloride. So the chloride was with the hydrogen. Now the chloride goes with the zinc. So what's zinc chloride's formula? What's the charge on zinc? What's the charge on chloride? So what's zinc is 2 plus, chloride is 1 negative. So what would zinc chloride be?
Chloride 2.
Right. Solid or aqueous? Good. What's the rule for chlorides? They're all aqueous except silver, lead 2, and mercury, remember? So yes, this would be aqueous because it's not one of those exceptions. Don't forget those, you got tests next week. Well, but on this, which is part of it, right? So. And what else would you make then? The chloride moved over and it left what behind? Hydrogen gas. And it's already balanced because they already put the 2 in here for you. Right, okay? So again, the chloride moved over, right? That's why it's a single replacement. Only one thing moved over. Okay, let's try another one. Name that first one. Magnesium bicarbonate, or you could call it magnesium hydrogen carbonate, but yeah. And HCl. Oh, now I have 2 things that are going to move, right? So this is going to move, and this is going to move. They're going to swap places, right? Double replacement now. So, what's the first product I will make? Magnesium chloride, yeah, MgCl2. Solid or aqueous? Again, they're all aqueous except for silver, lead, and mercury. That's not one of those, so it's aqueous. Hydrogen with bicarbonate. That's going to make our friend H2CO3 aqueous. Aha! But whenever I see that, I know I'm going to break it up and make it what it really is, water and carbon dioxide. But first, let's make sure it's balanced first, because it's easier to balance it and then break it up. I think it already is balanced, though. No, I lied. It's not balanced. Why is it? Okay, how do I balance this one? What'd you say, Jen? Or something? Right, I need 2 of these to balance it, I think. Because there was 2 H's and 2 bicarbonates made 2 carbonic acids. Okay, so now I'm going to say, aha, but I know it's not really that, so I'm going to scratch this out or erase it or do whatever you want to do and replace it with, it's really 2 water liquids and 2 carbon dioxide gases. Or you could just erase it. Whatever you want to do, I don't care. But just make sure you replace it with what it really is, okay? So again, so this is another reaction that bubbles and fizzes because you're making a carbon dioxide gas. The last one made hydrogen gas. This is carbon dioxide gas bubbling out, so you'd get. Okay, your turn. Try C. Try C. What'd you get for your products? 2 NaNO3s. Oops, wrong button. 2 NaNO3 aqueous. Thank you. Okay. Okay. Yeah, so you made 1 H2CO3, which you then broke down to make that, right? Perfect, good. Everybody get that? Or if not, do you know what's going on? Okay. Okay, we're moving right along here. Now, let me show you one last reaction with acids, and this is a true acid plus a base reaction. This is called a neutralization reaction. Just an acid reacts directly with the base. Whenever you have an acid reacting with the base, you always make water and some kind of an ionic compound, or what we call a salt. So the classic one is hydrochloric acid, which is an acid, sodium hydroxide, which we know is a base. When those combine, it is just a double replacement reaction. So the hydrogen and the chloride, oops, let me get up here. So the chloride and the hydroxide just swap places. So it becomes sodium with chloride and hydrogen with hydroxide, which is the same thing as water. Can you see how they just swap places? Just a standard double replacement reaction? No? Do you see that? Okay, so that's basically how that works. Let me see, get the next slide here. So you could imagine if I were to write, let's say, the net ionic equation. So remember how you do that? Take anything aqueous, you take it and break it apart into ions. Then you cancel out all the spectators. What's really left? Hydrogen, acid, plus hydroxide makes water. So that's the real net reaction for every acid-base reaction, is just acid plus base, hydrogen plus hydroxide makes water. That's really what happens. Let me highlight this. Acid plus base makes water. Which is why I told you way back when, again, you can always think of water as hydrogen with hydroxide. So let me just do a reaction here. Let's try this one together. KOH plus H2SO4. So we're going to swap the anions. I'm going to swap potassiums with hydroxide, hydrogens with sulfates. I'm going to swap the hydroxide and the sulfate. So I'm going to put potassium with sulfate. So what's potassium with sulfate? What's that formula going to give me? You are all over it, Stephanie. Awesome. K2SO4. Aqueous or solid? Aqueous. How do you know? Anything with potassium, always soluble. And then hydrogen with hydroxide. What will that make? H2O. Now, for balancing purposes, though, I'm just going to go ahead and just write the HOH up here, because it is helpful to balance it that way sometimes. So I see 1 potassium on the left, 2 on the right. So I'm going to put a 2 here. Now 2 hydroxides. But on the right side, I really only have 1 hydroxide. All right, so I'm going to have to put a 2 here, too. Now I've got 2 of these hydrogens, and I've got 2 hydrogens here, and then a sulfate and a sulfate. So that's balanced. So when you're balancing, I'm telling you, it's really super helpful to think of water as the H plus with the hydroxides. So balance the hydroxides with the hydroxides. Balance the H pluses with the H pluses. That makes it so much easier, I promise. Okay, your turn. Try the next one. Hydrochloric acid and aluminum hydroxide. See, I'm going to swap the hydrogen with the hydroxide and the aluminum with the chloride. So we're going to make aluminum chloride, and hydrogen with hydroxide is water. Again, for balancing, I'm just going to think of it as the hydrogen with the hydroxide. So 1 hydrogen, 1 chloride, 3 chlorides. So make it 3. Oh, now I got 3 hydrogens, so now I need 3 of these. 1 aluminum, 3 hydroxides, 3 hydroxides. Ta-da! Okay, and the last one, did you do it yet? Not yet? Okay, so some of you said yes, some of you said no. So, okay, I'll give you. So barium with phosphate would be Ba3 parenthesis 4. And that is a solid. Hydrogen with hydroxide is water. Now again, for balancing, it's so much easier if you think of it as H with an OH. So 1 barium, 3 bariums. So I'm going to make 3 bariums here. 3 times 2, that's 6 hydroxides. So I'm going to make 6 hydroxides. 3 hydrogens, 6 hydrogens, right? 6 hydrogens, not 12. Don't make it 6 times 2. Think of it separately. So 2, and then 2 phosphates, 2 phosphates. Yay, awesome. Okay, so let's do some calculations now here with these called titrations. So one handy thing we can do with acids and bases is you can take the concentration of one and find the concentration of another. So for example, oftentimes you can know the concentration of a base and use that to find the concentration of an acid. The way you do that is you know that when you add an acid to a base, you eventually make water. And at some point, it's going to be perfectly neutralized to where all the acid has exactly neutralized all of the base, and you just have salt and water left. So at that point, that is called the equivalence point. When the amount of acid or base you've added is exactly equal to the amount of acid or base that was there. So you've totally neutralized it, you made them equal, now it's pH 7, it's neutral. Pardon me, my cold is still not all gone, I've been talking too much here. You can just do lab. I don't have to talk during lab. So this point is where I've added exactly as much base as there was acid, or vice versa. So again, when they're perfectly neutralized, what do I make? Salt and water. So I just got water. So I just made pH 7. So that's called the equivalence point. Now the way that I can tell when that's happened is I add something called an indicator. We're going to use some of these today in lab. An indicator is something that will change color depending on the pH. The one we typically use is called, it's a big crazy name, called phenolphthalein. Phenolphthalein. And that is an indicator that will change color right when you get to pH 7. Actually, when you go 1 drop past, but basically we're at pH 7. So, it's clear, colorless, when you're in acid, and as soon as it hits pH 7, or that's just 1 drop past, it turns pink. So you basically know, so say for example you have acid and you're adding base. So I know it's clear, it's clear, it's clear. When I turn pink, boom, I know I must have added exactly as much base as there was acid. So that perfectly neutralized it and made pH 7. So that makes no sense until I show you a picture. Let me show you a picture. So let's say I have a little Erlenmeyer flask down here, and it has acid in it. I want to know, what is that acid concentration? I don't know what it is, but I know what the base is. So I start adding in the base. So you see in the flask, I have 5 acids, right? So just assume each one of those is a mole of acid. So let's say I have 5 moles of acid. So I add in 1 base, and that turns 1 acid into water. I add in another base, and that turns another acid into water, right? And I add another one, and I add another one. Well, at some point, if I've got 5 moles of acid, once I've added 5 moles of base, I've turned them all to 5 moles of water, and it's totally neutral. Boom, it turns pink. So when it turns pink, I know, aha, I added exactly as many moles of base as there were moles of acid. So the base is the known, so that lets me find the unknown, the acid. So let me show you that in actual calculation. It'll make a little more sense. So let's say I was doing this titration. It says 10 milliliters of acetic acid. I'm going to write that down here. So 10.00 milliliters of acetic acid and 0.22, oops, go back. That's not what I said. And then 37.55 milliliters of sodium hydroxide, which is 0.223 molar. The question is, what's the molarity, question mark, of the acetic acid? So, this looks an awful lot like the problems we did back in, what was that, chapter 8? Where you just volume to moles with molarity, mole to mole ratio, and then back again with molarity. They're exactly the same. Just now we're doing acids and bases. So, let me draw a little picture here. Are you still writing? That's fine. If you're still writing, go ahead and get started writing. Oh, wait a second here. What time is it? 4:38, okay. Okay, thank you for your permission. So, what this says is I have a flask over here, and in that flask I have put in 10.00 milliliters of my acid, right? So it's saying, then we took a big burette and we filled it up with 0.223 molar base. What was it? What was the base? Was it NaOH? Okay, NaOH. So I started out up here at 0 milliliters, and I added it in. Stayed clear, stayed clear, stayed clear, stayed clear, stayed clear, stayed clear, stayed clear. Suddenly, kaboom, it turned pink. When did it turn pink? It turned pink after I added 37.55 milliliters. Are you with me? So that's what it's saying. So after I added 37.55 milliliters of 0.223 molar, it turned pink. So that means however many moles of base I added must be exactly equal to the moles of acid that were in that flask on the bottom. That's why it does that. So let's go back here. I just lost my lovely drawing. Oh, don't want to do that exactly. Can I go back here? Oh well, whatever. So, okay. So let's start with what I know. 37. Whoops. I don't know why I put a decimal there. 0.55 milliliters of NaOH, and it's 0.223 moles NaOH per liter. So 0.223 moles NaOH per liter, or my little shortcut, a liter is the same as 1,000 milliliters. So, for every 1 mole of NaOH, I neutralize 1 mole of acetic acid, right? It's a 1-to-1 ratio. So, again, mole to mole ratio, just like we've done before 100 times. So, for every 1 mole NaOH, I neutralized 1 mole of acetic acid. I want to know the molarity of acetic acid. Molarity is what per what? Huh? Molarity, not molar mass. Moles per liter. Yeah, moles per liter. So now I have the moles of the acid. Right, molarity? You sit it right here. Moles per liter. So here's the moles. So grab my calculator. What's the moles? How many moles of acid do we have? Let's try this out. $37.55 times 0.223 divided by 1,000 times 1/1 does nothing. I got 8.37 times 10 to the negative third moles of acetic acid. So what you got? Anybody else? Okay. So I want the moles per liter. So here's my moles. Here's my volume. But I need that volume in liters, right? So let's turn that into liters. So 10 milliliters. 1 milliliter is 10 to the negative third liters. So 0.01000 liters. So my molarity is moles over liters. So moles, 8.37 times 10 to the negative third moles over liters, 0.01000 liters. And that gives me like 0.837. Some? No? Yeah, that should be right, I think. All right, I'm going to do it here anyway. Yeah, 0.837 molar. So, it's just like the ones we were doing in the past where you just use molarity to turn volume into moles, do mole to mole ratio, all that good stuff. But now, but in those we were trying to find the volume. Here we're trying to find the molarity. So, first we find our moles and our liters, and then it's just moles per liter. Molarity. Okay, you're giving me the crazy confused look. Never a good sign. Let's try one together. Let's try the first one here. Number 10 on your handout. Okay. Number 10. So, if the titration of 15.0 milliliters of hydrocyanic acid, need a little breaks in, requires 26.85 milliliters of 0.100 molar strontium hydroxide, what's the molarity of the acid again? Well, first we got to write a balanced equation so we know, is it 1-to-1, is it 1-to-2, is it 2-to-1, what is it? So we're going to write a balanced equation. So help me out here with some naming. Hydrocyanic acid. Hydroic came from cyanide. What's the charge on cyanide? 1 negative, so it must just be 1 hydrogen, so HCN. Reacts with strontium hydroxide. What's the charge on strontium? Find your periodic table. 2 plus, what's hydroxide? 1 negative, so we need 2 of those then. Okay. So we're going to neutralize those. So if I swap partners, what will I make? Water, yes. And Strontium cyanide. What's strontium cyanide? Yeah, SrCN2, right. So we've got to balance that. I need some Tues in places. Where do I need Tues at? 2 hydrocyanic acids and 2 waters. Because 2 hydrogens and 2 hydroxides has to make 2 waters. Okay, so, well, what do we know here? Let's see. We know 15.0 milliliters of this, and we want to know the concentration. We know 26.85 milliliters of this, and it's 0.100 molar. Right? Everybody have that written down? No? Okay, so I'm going to have to make a little room here, so I'm going to have to do some erasing, but you have that written down, right? Okay. So, 26.85 milliliters of strontium hydroxide, and there's 0.100, according to molarity, moles strontium hydroxide per liter, or 1,000 milliliters. So just to highlight this, right? This gave me that, right? The molarity gave me the moles per liter. Okay, good. Now, what's the relationship, though, between strontium hydroxide and HCN in our balanced equation? Yeah, mole to mole, which is what? 1 to 1, 1 to 2, 2 to 1, what is it? For every 1 strontium hydroxide, we neutralized 2 moles of HCN, right? So 1 mole strontium hydroxide per 2 moles HCN. So how many moles of HCN? Did you already do it?
0.00537.
Yeah. 5.37 times 10 to the negative third moles of HCN. So that's the moles. I want the molarity, the moles over the liters. So here's my milliliters. So I'm going to turn that into liters. Just for time's sake, I'm just going to save this little step here. 5.37 times 10 to the negative third moles over the liters. That would be 0.0150 liter if you did all that conversion. And we would get 0.358 molar, right? So this volume became this down here, right? Okay, questions? It's pretty similar to what we've done in the past, just slightly different. But still using molarity, still using mole to mole ratio. Okay, I want you to try one then. You try this one. Try number 11. Lithium hydroxide and hydrophosphoric acid. So write the reaction first. Notice it's hydrophosphoric acid, not phosphoric acid. Okay, so let me just check your balanced equation first. So what's the formula for lithium hydroxide? LiOH. Now here's the other one. What's hydrophosphoric acid? H3PO4 is phosphoric acid. H3P. Hydroic comes from ide, so just phosphide. Ide means by itself, just phosphorus by itself. So H3P. So you should get this. H3P plus 3 lithium hydroxides makes Li3P and 3 waters. Okay, we'll carry on from there then if you got that. If not, we'll make a little correction. Phosphoric is H3PO4. Hydrophosphoric, H3P. 43.5. Let's see. So, start with what I know. 10.0 milliliters of H3P. And the molarity is 0.145 moles H3P per liter, or again, 1,000 milliliters. And for every 1 mole of H3P, we got 3 moles of LiOH. And the LiOH is 0.100 moles per liter, or again, per 1,000 milliliters. So what did you say it was? 40 what? 43.5 milliliters. Sounds about right. So that was exactly like the ones in chapter, I think it was 8. Just volume to moles with molarity, mole to mole ratio, then moles back to volume with molarity. Okay, almost done. Let's wrap this up. Maybe have a little break and then do a little lab here. So I'm going to discuss, last thing is buffers. So buffers are really important, especially in your body. Your body has several what are called buffer systems. Now a buffer, what it tries to do is it tries to keep the pH constant. So it tries to neutralize any acid or base that you add either one. It tries to jump in and neutralize it, turn it to water, and keep the pH where it wants it to be. So basically what they are is it's an acid and its conjugate base in about equal concentrations. So remember, an acid becomes a conjugate base, a base becomes a conjugate acid. So you figure out what they are, and you use both of them. So then you have acid present and you have base present. So you might use, for example, you might use a weak acid. Let's say you use acetic acid. Or no. Let's say you use hydrofluoric acid, HF. Well, the conjugate base of hydrofluoric acid, HF, is just fluoride. So you might use hydrofluoric acid and sodium fluoride. So you have both the hydrofluoric acid and the fluoride, the conjugate base. You use them both that way. So why do we got to have both? Well, we got to have an acid and a base, because if I have a solution and I dump in some base, hydroxide, well, I need acid present in order to neutralize that and turn it to water. And if I do the opposite, if I add in base, well, then add an acid, then I need base present to neutralize it. So the buffer has both. It has acid to neutralize any base. It's got base to neutralize any acid. So regardless of what you add, it just neutralizes it, turns it to water. Neutralizes it, turns it to water. So it doesn't change the pH. It just keeps it nice, constant pH. Okay, let me pause while you're furiously writing there. Okay, so let me show you how this works. So, here's what we need. We need, like I said, just highlight this. A weak acid, whoops, and its salt, or a weak base and its salt. Okay, so we're gonna have, so let's look here at the next one. HCl and KCl. So, what kind of acid is HCl? Strong or weak? Is it one of our 6 strong or not? It is, yes. This is one of our strong acids. This is a strong acid. Okay, this will not work then. You can't use a strong acid and its conjugate base. It has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. So, let me show you something real quick. Let me just show you something real quick. I think I just blew your mind here. Let me show you how it works. Let me say the classic one is acetic acid, which is HC2H3O2. If you put it into water, what does it make here? Oh, well, it would make hydronium and acetate. So, here's my acid. Here's its conjugate base. So, if I was going to make a buffer out of that, I would try to mix 50-50 acetic acid and something acetate, like sodium acetate or potassium acetate or whatever. Then, regardless of what happens, I've got something there that can neutralize it. So, let's say I have this buffer and it's made up of both of these. So I got a buffer and it's 50-50. Acetic acid to acetate. And I come along and I pour hydrochloric acid in it. Oh, well, what can happen? Well, if I add hydrochloric acid, this base goes to work. The base jumps in and reacts with it. And it just neutralizes it and just reacts here and just turns it into H2C3HO2. So it just neutralized all the H plus. Well, I guess you have to make some chloride. But, so it neutralized the acid. So the acid didn't have any effect. The acid wasn't able to make H plus or hydronium or anything that would change the pH. Let's say I add a base. Let's say I add sodium hydroxide. All right, so I got hydroxide now. Oh, well, then the acid jumps in and neutralizes that. And I make sodium acetate and water. So again, it wasn't able to ionize to make hydroxides or anything, so it just totally neutralizes. So whatever I add, it just neutralizes both. And you see what's kind of cool is when the base got neutralized, it just made more of the acid. When the acid got neutralized, it just made more of the base. So it keeps on kind of like keeping the buffer going, keeps the buffer going. So it's very slick like that. So what we need is, though, a weak acid and its conjugate base. So how about the next one? H2CO3. First question, is that a weak acid or is that one of our 6 strong acids? Is it one of our 6 strong acids? No, it is not. Therefore, it must be a weak acid. Good. Okay, so that's good. Now, NaHCO3, is HCO3 the conjugate base of H2CO3? Yes, because if H2CO3 loses an H, it would leave HCO3. If H2CO3 acted like an acid, it would make hydronium and bicarbonate. So we have the weak acid, and we have the salt of the conjugate base. Yes, I have the salt, the sodium, with the bicarbonate. So I have everything I need for that one. I got the weak acid, and I got the conjugate base. So yes, that would be a great buffer. That would work fine. How about H3PO4? Is that a weak acid? Yes, this is a weak acid. Is sodium chloride the conjugate base of phosphate? No, right? There's no phosphate in there. So no, this cannot be the conjugate base. Chloride is not the conjugate base of that. Obviously not. So no, that would not work. No way, no how. How about the next one? Is H2C strong acid? That is weak. So is this the conjugate base of this acid? Yes, it is. You're thrilled, I can tell. So yes, that would work, because I could take that acid, and that's the conjugate base. You can make a buffer. Okay, let's wrap this sucker up. Let's land this plane. So I'm just showing you this. I already showed you this. It doesn't matter, as long as I can neutralize anything I want. Now we can also use this though to try to calculate the pH of a buffer. I'm not really going to do much of this. Just for let me just jump ahead and make sure I know what's going on here. So a buffer solution will look kind of like this. I've got the weak acid in the water making the hydronium in the conjugate base. So the Ka for that looks like just any other Ka, hydronium times the base over the acid. So I could rearrange that whole thing. Wait a minute there. I feel like I'm missing a slide here. Oh, no, here we go. Okay, yeah, no, I got it. Okay. So the hydronium is equal to the Ka times the acid concentration over the base concentration. And then once I have that, I just plug it in here and find the pH is the negative log of whatever that was. So you can kind of predict, okay, what pH is that buffer going to give me? And then I can kind of know, okay, so it's going to try to keep it at that pH. So just write down those two equations real quick, and then we'll just do a couple and land this plane. Okay, so let's look at this. So let's do an example. Okay. The weak acid H2PO4 negative, that's in your blood. It's part of a buffer between H2PO4 and HPO4. The Ka of that is 6.2 times 10 to the negative 8th. So if I make a buffer where it's 0.2 molar of both, what will the pH be? So we just said the hydronium is equal to the Ka times the acid over the base. So, what's the acid concentration? Oh, 0.20. What's the base concentration? 0.20. So, I can plug in both of those. And I would get, here's my Ka, right? 6.2 to the negative 8th. I plug in that. I plug in my 0.2s. Oh, those are going to cancel, right? 0.2 over 0.2 just goes away and becomes 1. So I'm left with the Ka. So what's the pH? What's the pH? The negative log of 6.2 times 10 to the negative 8th, which is 7.21. Okay, I know we're dying. We need a break bad. So let's just try this one, then we'll wrap it up here. What's the pH? This is our next, yeah, right here. What is the pH of a buffer made up of 0.2 molar H2CO3 and 0.1 molar HCO3 negative. So, the hydronium is the Ka times the acid concentration over the conjugate base concentration. So the Ka was given as 4.3 times 10 to the negative 7th times, what's the acid, what's the base? H2CO3, is that the acid or the base? That's the acid. Over, what's the base concentration? Yeah, 0.10 molar, right? Got that right? Yes. Okay. So, did you punch that in? So you're going to get, what's the concentration, I'm sorry? 8.6 times the negative 7, sounds good. So what's the pH then? The negative log of 8.6 times 10 to the negative 7th. So 6 point something. 6 point what? 07. Sounds good. Because there was 2 Sig Figs here, so 2 Sig Figs here. Okay, so that buffer then we'll try to keep that system at 6.07 best it could. Okay, let's wrap this up. We're all dying here. Now, one last thing. How do you know what combination to pick? It depends what your pH wants to be. So, let's say you want a buffer that'll keep the pH around 3.5 to 3.8. Well, then I need to pick a combination that's going to give me a pH of around 3.5 to 3.8. So, if I were to take the pH, just imagine the pH of these. Well, negative log of this one is going to give me around 4. Negative log of the next one is going to give me around 7, right? Do you see that? It's going to be around 10. So obviously the best choice to keep it in this range is going to be make that one. What is the negative log of 1.8 times to the negative 4th? I'm really trying to hurry here, I promise. 3.74. So that's right in the range where we want it to be, between 3.5 and 3.8. So yeah, so if I used a buffer that was made up of 0.1 molar formic acid, 0.1 molar formate, it'd be 3.74, it'd be right in the range. But if I did the next one, it'd be like 6 something. If I did the next one, it'd be like 9 something. So that wouldn't work. Okay. Okay, we don't have any. Okay, so hallelujah.